Bismillahirrahmanirrahim. The topic today is static loading on a bolted tension joint. We have already seen that bolts are preloaded. That is, even before the application of the applied load, there is a load Fi, tensile load in the bolt, and then the applied load comes into the picture, and that is P. And we know that the bolt ultimately has this force C P plus Fi, and C is the joint constant, and we know that it's a certain percentage of the load, applied load P. Now, whether such a joint under load Fi and then applied load P, and P is static, that is, it's not varying in nature, whether it's a safe joint or not, we have to find that out. And obviously we have to compare the stress produced because of these two loadings and compare them to the strength of the bolt. Now when we talk about the strength of the bolt, there's something called proof strength. Now, where it can be seen from this proof strength, it's in table 811, and you can read the value against the grade of the bolt that you are dealing with. Now, what this proof strength is, let's take a couple of minutes to see. I'm sure most of you are already familiar with the concept of proof strength, but those who are not will readily understand this. This is the strain axis, this is the stress axis. Now for any tensile test on a mild steel, you'll get some sort of this kind of figure. So it's impossible to miss the yield strength in this kind of a material. But bolts are not made of mild steel, they are made of high strength steels. So when it comes to high strength steels, in addition to some other materials, the stress strain curve is different, and the curve takes this form. There's a linear portion, and then it's like curved, and then it breaks here. This is the ultimate tensile strength. Now there's no one point where you can say that yielding has taken place. It's a non-linear kind of a curve and no distinct point of yielding here. So what we do, and you'll recall this from your first course in solid mechanics, what we do in this case is we take a value of strain, and normally we take the value of 0.2% of strain, or in other words a strain of 0.002, and what we do is we extend from this point. We draw a line which is parallel to the original stress strain line, the initial part of the stress strain line, and see where it cuts the original curve. And the point where it cuts the curve, this point, this is called the yield strength. The yield strength can be read off this point, against this point. This is the yield strength. Now, what we do in the case of bolts is, this is not proof strength, this is, we can say this is called 0.2% offset yield strength. It's a very useful concept for those materials that don't exhibit a precise yield point. Now this is 0.2% offset yield strength. What proof strength is, it is about 90% of this value. Roundabout. So what is happening here is you are talking about not this point, but you are talking about SP, and this is 90% of the yield strength, so it is less than the yield strength. Now what is happening here is we'll be dealing with, and it's established practice, we'll be dealing with not SY but SP. And so what it gives us is that if you design for SP, then you are already giving it a factor of safety against yielding. So there's another safety built right here. Now there's another point of departure for this in this case, and that is that table 8.11 not only gives you the values of the proof strength, but it also gives you the values of yield strength and ultimate tensile strength in addition to the proof strength, and these are all minimum values, not mean values. And this point is again of importance. All values taken read off the table 8.11, they are minimum values. So this is a departure from a usual practice where we, whenever we see a figure, we infer that it is usually at least 50% reliability. That is, 50% of the points will be above it and 50% below it. That is the mean value. Here it is, you can say that it is a minimum strength, which means that no, if you have a 1000 specimen and you break them, or you find the values of SP and SY, no SP, SY or SUT value will be below this. It is the absolute minimum. So there's another safety built in here. So you have these two levels of safety. So the result is that whenever you design something and you see that the factor of safety turns out to be small, 1.1, 1.2, 1.3, don't worry, because that is above these two safeties that are already built in. And we are going to talk about the factor of safety, what we need to consider before we can declare that a certain statically loaded joint is a safe joint. First of all, coming back to the loads, bolt has the load CP plus Fi after the application of the applied load, and the member has this value of loading. And obviously these two, and these are familiar for you, and these two equations only have meaning when members are still in compression. If you apply so much P that the members are no longer in compression, then these equations don't mean anything, because then there's no meaning of C. Whole of the load is then taken by the bolt. Now, first of all, we need to consider that yielding does not take place. So we call it the yielding factor of safety. Let's call this NP. P is for proof. We just saw that instead of yielding stress, yield strength, we take proof strength, which is slightly smaller than the yield strength. Now, for this, obviously, the strength in the bolt should be less than the proof strength of the material. Now, first of all, let's find out the strength in the bolt. That is simply FB over AT. AT is the tensile stress area, you know it. You can read it off table 8.1. So this is CP over AT plus Fi over AT. This part is called the induced stress, and this part is called preload stress. Now these are self-explanatory. Now you have to make sure that this sigma p, this doesn't exceed SP. So what you do is you bring in a factor of safety, sigma p SP over this yielding factor of safety, or in other words, SP will then take the form sigma b NP. Now what this means is that This NP, this is the factor by which you can increase the sigma B before SP occurs. This is the factor which basically, this is your safety factor. Now, putting in the values, put this equation, this value, sigma B value in this original one, and we get SP is equal to NP CP over AT plus FI over AT, which means that NP is equal to SPAT over CP plus FI. So this is the value of the yielding factor of safety. If we know the values of SP, C, E, FI and AT, we can know whether a joint is safe, and we can also know the magnitude of that factor of safety. Now there's another concept, and that is another kind of factor of safety, but this time it's not yielding, but it is called a load factor. It is similar but not the same, and it is, the symbol is NL, as opposed to yielding factor of safety, which sees by what factor the whole stress sigma B can be increased before we reach SP. Here we only talk about by what factor we can enhance the load P, applied load P. So this kind of factor, this does not take into consideration the preload FI. FI is there anyway. So FI, for certain FI and then applied load P, what increase in P can be initiated before we reach the proof strength of the material. So it only focuses on the applied load, not the total load. And for this, again, we put we use the same equation. Writing it again, CP over AT plus FI over AT. Now for sigma B, I'll put in SP. This is the ultimate limit, the limit which we cannot exceed, and then we apply this load factor NL only to the applied load P, not to FI. FI remains as it is. So this gives us a value of NL equal to SPAT minus FI over CP. This is another factor of safety that we use. There's a slight difference between the two. One deals with the total load. The other one, the second one, load factor, only deals with the applied load, not the FI. It considers FI as constant. It is going to be there anyway. So it only considers the load P and any increase that we can add there before this whole thing exceeds or equals the proof strength of the material. Now the third thing to consider here is not strength related at all. It is the joint separation factor. Recall that all these equations, for example, this equation, I'm going to write it again, FP CP plus FI, FM1 minus CP, I'm sorry, this is not plus, this is minus FI. Both these equations only have meaning if FM is less than 0, that is, there's still some compression in the joint. Now this joint separation factor makes sure that you still have a compression, because if there's no compression, then the whole of the load goes to the board and it is not a joint to start with. Now this is called N0, and When do we know joint separation has taken place? When this Fm becomes 0. The moment it becomes 0, then there's no compression there. So putting in the left hand side 0, and then writing the rest of the expression 1 minus c, and then we applied again this factor also applies only to the applied load, not the initial load that is there, preload that is already there. Okay. So this, and then this n naught becomes Fi 1 minus c p. So this is the third factor. If we can say with confidence that these three are not something to worry about, then this joint is safe from a static loading point of view at least. So before we move on to a numerical problem, let's take up another related thing. What kind of preload Fi we can put on a certain bolt? Magnitude of Fi. Obviously, these factors of safety, they tell us about load P, what kind of P we will apply, and the whole thing becomes problematic. For example, it yields or joint separation takes place. But what about magnitude of Fi? What sort of Fi should we put on a joint first? Because P will be applied later on. So there are guidelines for this, and these guidelines are Fi is equal to points, and these are again empirical. These things work. Fi is equal to 0.75 into Fp. Now Fp is the proof load, and obviously you can calculate this proof load from proof stress and the tensile stress area. It is 0.75 of Fp for non-permanent joints, that is reusable joints. If you are going to open and close them again and again, then you should load that bolt to 75% of its proof load. And if it's a permanent joint, you're not going to open it again and again. Once you close it, that's it. Then you can go up to 0.9. Obviously, we are not going up to 100% because recall P is going to be applied over and above this. So you cannot exceed at this stage the yield strength. Now, these equations are equation 831, and obviously it's a simple matter that Fp is a load, whereas you'll be reading the values of proof strength, not proof load. So proof strength Sp will be given from table 811, and then you simply multiply with 80. This is the tensile stress area of the bolt in question, and you can get this Fp. Now this is table 811, and 80 is table 81.